Hello, this is the presentation for the final project of the course ECE 570 to be talking about point pillars for vehicle detection on 3D point clouds and implementation from scratch done by myself. Well, what is point pillars? Point pillars is a full end-to-end deep learning algorithm for 3D object detection from point clouds. For this implementation, we're only going to be focusing on detecting vehicles, and well, the algorithm is very convenient because it can represent a 3D point cloud into a 2D pseudo image, and on this 2D pseudo image afterwards, computationally efficient 2D convolutions can be applied, and this makes inference time and training time much faster. That is something you need for autonomous vehicles. Well, these were the components of the neural network that had to be implemented by myself. We start with a raw point cloud. This raw point cloud is then voxelized using pillars. So pillars are infinite height prisms. Each pillar contains certain number of points from which features can be learned by applying 2D convolutions in the pillar feature net. This generates a pseudo image that is then passed to the backbone, and the backbone applies feature extraction at different scaling levels at half, a quarter, and an eighth. Then each block is upsampled using a deconvolution layer, and the upsample results are then concatenated, and this is going to contain all the extracted features that are finally passed to a detection head, a single shot detector that can then do the prediction for the regression and classification targets. The main goal is to implement a 3D vehicle detection algorithm for an onboard LiDAR sensor on an autonomous vehicle. In this case, the Kitty dataset, the 3D Kitty dataset was used. And well, this is important because perception modules are very, very important for self-driving cars. Autonomous vehicles must be able to perceive their environment. So this is why this is important. These are some implementation details. P was set to 12,000, N to 100. D are the augmented dimensions. Each point is represented by its XYZ coordinates. R is reflectance. XC, YC, and CC are offsets from the pillar point's mean, and XP and YP are offsets from the pillar centroid. More than 30 epochs were used, and validation was done every 2 epochs during training loop. The Kitty dataset was used a reduced version, and the optimizer used was Adams with a scheduler to reduce the learning rate every certain amount of epochs. These are the results. To the left here, we can see that the loss function effectively went down during training time for a little bit more than 30 epochs. Also, the loss went down in the validation set. The average loss was 1.55, and to the right, we see a visualization of a 3D point cloud represented as a 2D pseudo image. The grids are the anchors, and the red boxes are the ground truth boxes. So, well, final thoughts on this. This was a challenging reimplementation because this neural network has a lot of components. More than 2,000 lines of code had to be developed. And it was challenging because pretty much no borrowed code was used. The only borrowed code that was used was a preprocessing script for the Kitty dataset that pretty much just got rid of the areas of the point cloud where there were no annotations. And well, at implementation level, there are definitely more considerations that have to be taken into account. This project is definitely a step behind implementation level. It is close, but it is not quite there. There are still more considerations. And well, another layer of difficulty here is that training time is very, very long. Simple training could be at least 6 hours, but really to get better results, you'll need at least 24 hours. So it was very time consuming. And for future work, the idea is to be able to implement this algorithm on the Dallara AB21, that is a very particular vehicle that competes in the Autonomous Challenge autonomous racing competition. So thank you very much.